Good morning. Today we are going to discuss about Unit 4 special semiconductor devices. In that we are going to see about tunnel diode or Eseki diode. So tunnel diode is a thin junction diode which exhibits negative resistance under low forward bias conditions. An ordinary PN junction diode has a impurity concentrations of about 1 part in 10 power 8. But in the tunnel diode we have a 10 power 3. So compared to that, this is a less impurity concentrations, but we are using in the oscillator circuit like that. The width of the junction barrier varies inversely as a square root of impurity concentration, and therefore it reduced from 5 microns to less than 100 amps. This thickness is only about 1 part of 15th of wavelength of visible light. So for such thin potential energy barriers, the electrons will penetrate through the junction rather than surmounting them. So this is a symbol of tunnel diode. It shows generally it is made up of germanium and gallium arsenide. It is introduced in 1958 and introduced by Leo Eseki. So that only first they are used as Eseki diode, and then later we have changed that tunnel diode like that. The next thing we are going to discuss about what is tunneling. So this tunneling, it is mainly a potential energy, how much potential energy it is going to be increased or decreased, like that only we are going to discuss about. Classically, the carrier must have energy at least equal to potential barrier height to cross the junction. But according to quantum mechanics, there is a finite probability that it can penetrate through the barrier for a thin width. This phenomenon is called tunneling, and hence the Eseki diode is known as a tunneling diode. The quantum mechanical behavior is referred to as tunneling. These high impurity density PN junction devices will be formed as either highest form of energy or else lowest form of energy only. This quantum mechanics is analyzing. And the next one, characteristics of tunneling. First, IP is peak current, IV is valley current, VP is peak voltage, VV is valley voltage, and VF peak forward voltage. That there is a two condition we are going to discuss in the characteristics of tunneling diode. First forward current rises sharply as applied voltage increased, where it would have risen slowly for an ordinary PN junction diode. So this major cutoff regions, it has shining light up to that it is increasing. Also, reverse current much larger for comparable back bias than in other diodes due to the thickness junction. So here we are just using for forward bias current. If I am going to increase, that means the current has increased, it has slowly risen, and then after that if the current as I am decreasing means it is slowly decreasing like that valley point like that. The interesting portions of the characteristics starts from 0 to A on the curve, that is the peak voltage, As the forward bias is increased beyond this limit, the forward current drops here and continues to energy band diagram. So this energy band diagram we are going to use for low regions to high regions, how it is moving that. So here also the shaded areas show the energy states occupied by electrons in valence band, whereas the cross hatched regions represent energy states in the conduction band occupied by the electrons. The levels to which energy states are occupied by electrons on either side of junctions are shown by dotted lines. When the bias is 0, these lines are the same height unless energy is imparted to the electrons from some external source. The energy possessed by the electrons on the n side of the junction is insufficient to permit to climb over the junction barrier to reach the P side. So the conduction band to V side, it is diffused that N region to P region. However, the quantum mechanics shows that finite probability for the electrons to tunnel through junction to reach the other side. At the zero bias, zero current on the IV diagram, all the energy states are filled below Fermi level of energy both sides of the junction.